So when you talk about crystal structure, basically what this means is in a solid, there is a pattern. Okay, you have atoms in solids and these atoms form a pattern or arranged in a particular pattern. So we are talking about a pattern or a regular periodic arrangement of atoms which will give rise to a particular structure, what we call as the crystal structure. But that is not all, because we need to understand how a crystal structure is formed. I mean, what is the basis of that? So if you want to understand that, you have to understand few more terms. First of all, you need to understand what is a crystal, and in order to understand this, you also have to understand another term known as lattice. Okay, so these are the two terms that you would come across first when talking about crystal systems or crystal structure. Okay, and please do remember that these two are different. If I define them from that angle also, from the definition also, it might apparently look similar, but please try and understand that these two are different. Then only you would be able to appreciate the real meaning of crystal structures. Okay, so if I define crystal, it is basically a transnationally periodic arrangement of atoms in space. And lattice is a transnationally periodic arrangement of points in space. So if it is just points, that is the lattice, how do you get to the crystal from this? Because lattice does not talk about atoms, it is saying that it's a periodic arrangement of points. So that means to each of these points we need to assign an atom, something that can be repeated, right? And that repetition in 3D will give you the entire crystal structure. So with lattice we need something, lattice plus something which can be repeated in a periodic manner to generate the crystal structure. So that something is known as a motif. Okay, motif can be defined as an atom or a group of atoms associated with each lattice point. So basically, motif is the repeating pattern or the repeating unit of the pattern. So if you have a pattern, how that is repeated, the motif will tell you. Okay, so lattice tells you how to repeat, or in other words, you can also say that lattice is the underlying periodicity of the crystal, right? On the other hand, motif tells you what to repeat. So when you want to define a crystal, both of these information are required. So what does it mean basically? It means that when you combine the lattice with a motif, you generate the crystal. So here we have a lattice, a periodic arrangement of points, and when we assign one diamond here to each of those points, we generated the diamond pattern, which is basically that structure or the crystal that we are looking for, right? So to obtain the crystal or the crystal structure, you need a lattice and you need a motif. Okay, lattice will tell you how to repeat and motif will tell you what to repeat. All right. So diffusion is basically transport of matter. Okay, when there is something that has to move, the matter has to move in a substance, then it occurs through a process which is known as diffusion. Okay, so this is essentially mass transfer. And whenever there is a movement of matter, it is always from higher to lower concentration. So basically what we are saying that you have a gradient in the concentration. So this transport occurs under the influence of a concentration gradient. And therefore the transfer will occur from higher concentration to lower concentration. Okay. So when you say mass transfer in a material, it essentially means that a set of atoms are moving from the higher concentration side to the lower concentration side. Okay. So let me tell you what I mean by this concentration gradient. Okay. So as I said, this transport of matter or mass transfer means that a set of atoms will move from the higher to lower concentration. Okay. So in any part of the substance, if you have a higher number of atoms, like this part, for example, the part on your left, you can see with the help of those red dots, those red circles, which indicate the presence of atoms. On the left hand side, you have higher concentration, right? So the atoms will move from left to right in this case. So the concentration gradient is along this direction. Okay. This could be similar atoms. For example, in a pure metal, you have only one type of atoms, and in that case, it is self diffusion, because only one type of atom is moving in the same material. But if you have an alloy, then one type of atom can move into another type of material, right? A can move into B or other way around, right? So if you have an alloy between A and B, B atoms can move from one region to another region under the influence of that concentration gradient. Okay. So if in a portion B atoms are more, and in an adjacent region, if the number of B atoms are less, there is a concentration gradient, and B atoms will move across that concentration gradient, right? So that is another type of diffusion where you have two different species to talk about in terms of their movement across a concentration gradient. Okay. But whatever it is always from that higher concentration to lower concentration side. That is the direction of the motion of these atoms, right?
The technique is called dynamic light scattering,
Or DLS in short.
Why it is called dynamic, that will be clear in a moment as we progress. So this technique uses the scattering of light by the particles to measure the particle size and the size distribution as well. And it is a common practice to disperse these particles in an appropriate solvent and get a good suspension, which is used to derive the particle size. Now, when the particles are suspended in a liquid, they are not stationary, and this motion of the particles in the solvent is known as the Brownian motion. So Brownian motion is nothing but the random motion of particles dispersed in a solvent in all directions, as you can see from this animation over here. And this motion arises due to the collision of particles with the solvent molecules. Now, this collision causes certain amount of energy transfer, which is more or less constant, and therefore the smaller particles will move faster compared to the larger ones, as you can see from this animation over here. Now, this velocity of the Brownian motion is defined by a property known as translational diffusion coefficient, written as d. And the d is related to the size of the particles by the Stokes-Einstein equation, which is given as follows, wherein dH is the hydrodynamic diameter. So here the particle size is defined by this hydrodynamic diameter, and I'll come to that in a moment. K, as you know, is the Boltzmann constant, and eta is the viscosity of the solvent. Now, this hydrodynamic diameter is defined as the diameter of a sphere that diffuses at the same rate as the particle being measured, right? So that is how the size of the particle in this case is defined, and that can be obtained from this Stokes-Einstein equation, wherein all the parameters such as K, T, T here is the absolute temperature, and eta are known. So if we can derive this translational diffusion coefficient D, then this particle size can be obtained from this equation. Okay. So this dynamic light scattering technique will essentially try and measure this diffusion coefficient so that we can use this Stokes-Einstein equation to derive the size of the particles.